Hey everyone, welcome to the late night version of Computer Science 3200. Had to move the lecture because I had a technical difficulty this morning with one of my hard drives that I record the lectures to. So I had to make sure to get that working beforehand. But of course, since we're pre-recording things, since we're recording this and posting it on YouTube, then if people can't make it to the later lecture, then that's fine. How's everyone doing out there? Is it too late for you? Someone out there says, have you guys tried to implement the optimization of not copying the state? I feel like it's going to make use of undo action, though that is a wise feeling. I can confirm that that might be the case. So, today we're going to be doing some cool stuff. So if we look over here at the schedule of where we are, we're just past the halfway mark in the course. I think the last lecture was actually the halfway mark. And if you saw the D2L post or the post on Discord, I've actually given 2 extra days for the due date of assignment 3 because a lot of people had midterms that overlapped with assignment 3. Like you can see, for example, that our own midterm overlapped with assignment 3. And so I'm giving people until Saturday night to finish that if they need it. And today we'll be releasing assignment 4, but you have more than enough time to do assignment 4. I think assignment 4 is the easiest assignment of all. It's and I'm going to be explaining that in the second half of this lecture. So since it's late, let's just jump right into it. So what I'm going to be talking about at first is genetic programming. And genetic programming is a form of evolutionary computation that we talked about last time. And then once we're done with genetic programming, I'm going to hop right into assignment 4, which I'm sure that people are most interested in. So let's go ahead and do that. All right, so genetic programming. What is the motivation for genetic programming? We've also already saw genetic algorithms and other forms of evolutionary computation, but why specifically do we want to do genetic programming? So first, we can use it to do automatic programming. So we can use genetic programming to program a computer to learn to program itself, which is the craziest thing I've ever heard. But it's possible, and you'll see how by the end of the lecture. We can also use genetic programming for machine learning. So machine learning is a study of computer algorithms that improve themselves automatically through experience. So we have different types of problems such as classification and regression and function approximation, and we can do all of those things with genetic programming. So what we're going to do in GP is we're going to introduce a population of computer programs that improve automatically as they experience the data on which they're being trained. So unlike genetic algorithms, genetic programming actually requires a training set again. So this is, genetic programming is more a form of machine learning than a genetic algorithm would be, for example. But genetic algorithms are still, you can consider all of evolutionary computation as a form of machine learning. It's just that genetic programming requires a training set. So just a quick touch on machine learning and how it relates to genetic programming. So in machine learning, you're going to have some sort of algorithm that does training, testing, and possibly cross-validation. So, for example, there's supervised learning, and in supervised learning, each training instance is given correct outputs. So you may be given, for example, a bunch of images, and then labels on those images, like this is a cat or this is a dog, and then as the outputs, and then you'll have to learn which images are cats and which images are dogs. But the important part in supervised learning is you are given what the correct output is. In unsupervised learning, you are not given correct outputs, but instead, in unsupervised learning, you're trying to discover patterns in the data. So, for example, clustering algorithms are a method of unsupervised learning. And then in reinforcement learning, which we'll get into in the next lecture, so the rest of the course will be in reinforcement learning, what happens there is that agents are going to interact with their environment and get a reward signal. And then based on that reward signal, they're going to do things more often or less often in the future and eventually learn how to accomplish their goal. So in machine learning, there are different types of problems, especially these are the classical types of problems in supervised learning. So in classification, you may have a situation like this, where you have two types of data, and you're trying to learn, for example, based on the XY coordinate of the point, whether or not it's a blue point or an orange point. And so you would feed in the XY coordinates and blue or orange as the labeled training data, and then your model would somehow learn to predict the color of newly inputted points. In regression, you have sort of a continuous output, whereas in classification, you're deciding between a bunch of classes of object like blue point or yellow point or orange point. In regression, you're essentially learning the output of a function. So for example, here, if you fed in a bunch of points and their values into like a bunch of x values and the corresponding y values of the function that you're trying to learn, then the regression algorithm would learn this sort of line of best fit. So if you've ever done in Excel or in Google Sheets a line of best fit, that's usually some form of regression, usually a linear regression. Unsupervised learning can be thought of, clustering is a good example of those. So if I give you a bunch of points in a graph and then say, okay, cluster this into 10 sets of points, then unsupervised learning would be a good way to approach that. Also, machine learning can be used for dimensionality reduction or function approximation, so you can map high dimensional inputs into a lower dimensional space. And of course, with machine learning, there are hundreds, if not thousands, of different machine learning algorithms. But lately, in the past 5 to 10 years, neural networks have really become the standard in machine learning. And so no, when we say machine learning, we don't mean only neural networks, but certainly neural networks and deep learning are a huge part of modern machine learning. But we're not learning that yet in the course. So a bit of an overview of genetic programming. It was developed by John Koza in the 1990s and his research group. And it's typically applied to machine learning tasks. So some attributed features of genetic programming, it can compete with neural nets in some areas. Deep learning has sort of taken over in terms of raw results, but there are some areas where genetic programming still does better than neural networks. In practice, it needs very large populations, and therefore it's kind of slow. And we also have nonlinear chromosomes or nonlinear genes, and we'll get into what that means. But for example, in our genetic algorithm, we saw that our gene was just an array of integers, but now we're actually going to have trees or graph structures as our genes in this. So a bit of a technical summary of GP and how it differs from other types of EC. So as I said just then, our representation for our genome is going to be a tree structure rather than just an array. Our recombination, instead of doing crossover, we're going to do an exchange of subtrees in the tree for the parents. In our mutation, we can have random changes in the trees rather than just having random integer changes in a genetic algorithm. And our parent selection can be fitness proportional, so we can do roulette wheel selection, again, in GP as well. And survivor selection, we're not going to get into too much survivor selection in this course, but typically in GP they do something called generational replacement, which I don't need to get into the details of. So let's give a quick example of genetic programming. Credit card scoring. Okay, so if you're working at a bank or you're working at a credit card, oftentimes you want to give your customers some sort of score in order to be able to say, we want to give a loan to this person, or we really don't want to give a loan to this person. And so if we want to distinguish like good candidates from bad candidates, how can we do that? Well, one way to do that is to hire somebody to sit down, and every new application comes in, you have a human being look at it and sort of use their experience and training to say this person is a good candidate or this person is a bad candidate. But what's been happening for many, many years is that there are functions that approximate whether or not you're a good candidate or a bad candidate, and based on your properties as a human being, they give you a score. And it's kind of sad in a way how your ability to like buy a house is reduced to some function maybe in a neural network, but that's the way she goes. That's just how it works, right? I don't know if any of you are old enough to be really worrying about your credit score yet, but when I graduated with a student loan, my credit score was not very good. So maybe you should look into that soon. So here's an example of this credit score stuff. So you're going to have a table of values, of categories of values for each person, right? So for example, maybe person number 1 has 2 children, their salary is $45,000 a year, their marital status is married, and now we have the training data or the labeled output, which says whether or not this person is okay to give a loan to, okay? So these values are just made up, okay? I took them from an example in a book. So no, this is not me saying that these people are okay for a loan or not, but there may be other factors that aren't listed in this table that are taken into account as well, but just for this example, we'll look at these. So for example, this person with no children and a slightly lower salary who's single, maybe they're okay for the loan, right? So we have, in genetic programming, we are going to be doing training on a training set of labeled data. So let's just say that one possible model that a human being might come up with if they were applying this, that maybe over the experience of their lifetime, they've shown that if someone has 2 children, so NOC, number of children, and their salary is greater than $80,000, then they're good for a loan. Otherwise, they're bad. We don't want to give them a loan, okay? So this is completely made up. These are just randomly selected numbers. And so in general, what we have is a formula that says if the formula is true, then it's good. Otherwise, it's bad, right? So we have some possibly complex formula in which we evaluate someone's credit score, and it's good, or otherwise it's not good. And the only unknown here is the right formula, right? We're trying to figure out this formula. We may not know it, but we do have this training data. And so if I gave you, a human being, this training data and said, try to come up with the formula, what you would do is you'd sort of play around with these if statements and say, okay, maybe this person is not okay here. So maybe if they had more salary in another instance, or maybe if the person has 0 children, then they're always okay. So you would be trying like all possible formulas to figure out whether or not someone is okay. You're trying to come up with that formula. And so what we're trying to do here is use genetic programming to do machine learning to come up with a tree structure which represents a formula for whether or not someone should get a loan. So whether their credit score is good or credit score is bad. And so our search space, which is the phenotypes, is the set of all possible formulas, okay? So the set of all possible formulas that you can do, that's the thing that we're searching over. And the fitness is going to be the percentage of well-classified cases of the model that it stands for. And what this means is that our fitness is, let's say we have 10 examples here, right? So a fitness is going to be, we ran our formula, that's our current individual in the genetic algorithm, and however many matches it got with whatever the training data was, that's going to be our fitness. So the more matches to the training data, the better the fitness. Okay, and the representation for our formulas is going to be something called a parse tree. So what is a parse tree? Well, here's a parse tree. It's a way that we can represent Boolean formulas, or basically all mathematical formulas, as a tree structure. So let's look here. So we have this formula that we're trying to represent as a tree. So if number of children is equal to 2 and S is greater than 80,000, then good, otherwise bad. So here we have that tree structure. So we have an AND up at the top, right? So that is our top level operator. Then we have number of children equal 2 and S greater than 80,000 as sort of our leaf nodes. So here, when we break it down into these parentheses, we have an operator and we have 2 variables into that operator, right? So the operator is equals. the first variable is number of children and the second variable is 2. So if number of children equals 2, that is what this returns a Boolean, yes or no, okay? And down here we have the same thing, but for s greater than 80,000. So if s is greater than 80,000, this will be true. And then the AND gets applied to the results of these. And so we'll say number of children equal 2 and s greater than 80,000. So that is how we take one of these formulas and we break it down into a tree structure. And these tree structures are a universal form, okay? So we can represent a bunch of different things, like, for example, this mathematical formula here can easily be represented as a tree structure. We can also have programming code be represented as a tree structure. We can have arbitrarily long Boolean values represented as a tree structure. And here's another example, okay? So here we have a mathematical formula, and we're going to take this and we're going to break it down into a tree. So how would we do that? Well, there's actually no single tree that you have to apply here. There's a bunch of different trees that could give you the same answer, and this is one of those trees. So let's just have a look at that. So let's look at the 2 times pi plus, and then we have a bunch of stuff in brackets. So essentially what we have here is we have something on the left plus something on the right. So we're going to break this down into the leftmost thing, and we'll break this down into the rightmost thing. So 2 times pi. If we look over here, we have our 2 times pi, and that's the thing on the left of the plus, right? Now we have something that's on the right-hand side of the plus, but that itself is another formula that we have to break down. So over here we have x plus 3 on the left-hand side of a minus, and then y divided by 5 plus 1 on the right-hand side of the minus. So down here we have the minus, on the left we have the x plus 3, and on the right we have another formula, right? So we have a y on the left-hand side of a divide, and a 5 plus 1 on the right-hand side of a divide. So here we have y divided by 5 plus 1. So this is how we break down these formulas into a tree structure. So now we would be able to use this tree structure to learn arbitrary formulas with genetic programming. Similarly, we could do the same thing with a Boolean function, and I'm not going to break all this down because we just did that. But the cool thing is we can also break down code like this. That is really, really cool. Okay, so if we have semicolon, if we introduce semicolon as an operator here, we can actually represent this code as a tree structure. So for example, I equal 1 colon, right? I equal 1 colon, and then we have a while, and on the left-hand side of the while is the condition, and on the right-hand side of the while is what happens inside the while loop. So we have I less than 20, that is the condition for the while continuing, and then I equals I plus 1 as what happens inside the while loop. So this is really fascinating. So you can literally run a genetic programming program to find programs. It's so cool. It's like the computer is finding out its own source code, right? It's writing programs for itself. It's so interesting to me that this is even possible, but this is how it's possible. So how do we talk about the representation for the GP then? Well, in GAs are genetic algorithms, chromosomes are linear structures. So we saw vectors or integer strings or permutations, right? We just had this one-dimensional array structure that we held things in. Tree-shaped chromosomes are what we'll be using in GP, and they are non-linear. So in genetic algorithms, the size of the chromosomes is fixed, but in GP, the size of our chromosome is not fixed. It may vary in depth, in width. It may be like a giant tree with 300 nodes, or it may just have 1 or 2 nodes. So that's a very important thing to keep in mind. Also, we have a set of what are called terminals and functions. So our symbolic impressions are defined by a terminal set, T, and a function set, F. So terminals provide value to the system. They're comprised of the inputs to the GP program, the constants, and the no argument functions. And the functions are a process they process a value already in the system. So they're comprised of the statements, operators, and functions available to the system. That's supposed to be GP system. So Boolean, or, and, arithmetic, plus, divide, conditional, controls, loops, etc. So really quickly, we need to initialize the GP tree as well. And so we're going to set a maximum initial depth of the tree, call that dmax. And then we have a full method here in which each branch is going to have a dmax. And so what we do is we say if we're using the full method of initialization, then we're going to essentially randomly assign interior nodes to be functions, like plus, minus, whatever, and we'll randomly assign terminal or leaf nodes in the tree to be from the terminal set. So these will be actual values, and I'll show you what this means in a second. Or we could use the grow method, which doesn't fill out an entire tree necessarily. So what we do is we essentially, at each node, we choose randomly whether or not we want to grow the tree or stop the tree right there. So one common way to initialize genetic programmings are sort of half and half, where we grow and null and deliver half of the population. Okay, so that's supposed to be full. That's why that didn't make any sense. Let me change that real quick. Yeah, so where grow and full each deliver half of the population. And what that means is that half of the population is initialized by the full method and half of the population is initialized by the grow method. So again, the full methods develop entire trees up to dmax, and grow methods may vary in the number of branches that they have and the depth that they have up to dmax. Okay. And so what we get here, what I said before, is each of the leaf nodes are values, okay? So the leaf nodes in these trees have to be concrete values like 5, 3, x, pi, whatever. But the interior nodes, the non-leaf nodes, are functions or operators, okay? So that's how we define these trees. And we can see these values here. And also, what this slide is trying to say is that the mutation operator is different than it was with GAs. So we could replace randomly chosen subtrees by new randomly generated trees. So think here, for example, if we took this tree, which is 2 times pi plus x plus 3 minus y divided by 5 plus 1. If we took this subtree, so let's randomly select an interior node and replace it with something else. So over here, we take this node and we replace it by the value y. Okay? So when we do that, this is what we get. So when we mutated this tree, we happen to get this mutated tree. Alrighty. So the mutation has 2 parameters then. It would be the probability, PM, to choose to mutate versus recombine, and the probability to choose the given subtree to replace. So that means that if we have a tree, we first have a probability of whether or not we're going to mutate the thing in the first place, and then we also have a probability of whether we're going to individually mutate each interior node. So in more recent literature, one of the interesting things is that the probability to mutate something should actually be very, very close to 0. We don't want a lot of mutation going on with genetic programming, but we do want a lot of mutation going on with genetic algorithms, which is just an interesting result of doing lots of experiments. And also something interesting is that the size of the child can exceed the size of the parent, whereas in genetic algorithms, the size of the child is the same as the size of the parent. And in recombination, the common thing that we do is we just exchange 2 randomly chosen subtrees among the parents in order to form a child. So the recombination has 2 parameters, which is the probability to choose recombination versus mutation, and also the probability to choose an internal point to set it as the crossover point. So what does that mean? It means that if we had 2 parents, for example, this tree and this tree, what we would do is we would randomly choose internally one of the nodes inside each parent, And then we would take this subtree and put it over here to form one child. And we would take this subtree and put it over here to form another child. So for example, where we have a times 3, we would replace it in here, and then we'd get this subtree, right? And over here, where we had the a plus 3, or a times 3, we would now replace it with this subtree, and we'd get this child. Okay. The last thing we need to talk about is how we actually evaluate the fitness of genetic programming. The fitness is how we actually not only measure the quality of our solution, but also how we choose to measure the quality of the parents for breeding selection. So the fitness is how well the program has learned to predict the outputs from given inputs. It's designed to give continuous feedback about how well a program performs on the training set. And so what we're going to do is we're going to use error-based fitness functions, such as squared errors or root squared errors or squared root errors, etc. So here's just an example. We could have the number of matching pixels in an image matching training task. Or we could have the number of walls hit for a robot controlled by a genetic program. The number of correctly classified examples. So for example, if there were 100 examples and we correctly classified 95 of them, then we would have a very good fitness. We could have some sort of deviation between the predicted value and the reality. So rather than the number of correctly classified samples, we could take the error of the correctly classified samples. Maybe we could have the amount of money that was won in a betting game, or we could have the amount of food that was eaten in some amount of time, okay? If we're talking about life simulators, etc. So, here's the generational genetic programming, which is exactly the same as the algorithm for genetic algorithms. So we're going to initialize the population with some random individuals, then we're going to repeat forever. We will evaluate the population for the fitness, select the parents with the highest fitness, combine parents to form offspring, mutate the resulting offspring, and then the next population we will somehow be choosing from the population, the previous population, the offspring, and the parents, etc. So for example, if we wanted to do something like symbolic regression, so if we wanted to learn this function, right? If we wanted to have our GP learn this function, then what we might want to do is say, okay, our terminal set will be consisting of the x variable and some constants, right? Because we've got constants here, 2, 2. So we do have to choose some finite set of constants when it comes to GP. So here we've just chosen -5 to 5. We may have addition, subtraction, multiplication, and division. And this is protected division, so we can't divide by 0. Our fitness is going to be the root mean squared error over 10 training cases. And then we have a bunch of parameters, which are the population size, the initialization method, the crossover, mutation rate, etc., etc. So in here, what we would have is some sort of training set. And in the training set, we would have a bunch of inputs and the correct output. So what this is over here, it's a bunch of input values, and then the output is what you would actually get if you ran this function on the input. And then we're going to run our genetic program on this training set to see whether or not we can match the given output. So just for an example, here's what we might have as the best individual from generation 0. We could say x divided by 4 minus x over 4, or some weird formula that sort of kind of gets close, but not really. Now maybe in the next generation, what we could have is like a very large formula, which sort of, comes close to an approximation of the formula, but doesn't get it exactly. And then maybe like here is it from generation 2. And then eventually, if we did get the exact formula, then what we would have is something like this, where we have the exact formula, which is x times x divided by 2, right? So that's what would happen there. So that's what genetic programming is. It's really fascinating, and I actually have not implemented genetic programming before, and I would really like to try sometime. I just have to find enough time. So that's genetic programming. We will not be implementing genetic programming, but it could pop up on the final exam as a question. Okay, so know what's going on in genetic programming is what I'm saying. All right, so that is it for the lecture slides, and now we're going to get right into the assignment. Okay, now the fun stuff starts. Here's the assignment. We are going to be writing a genetic algorithm Sudoku solver. So if someone has not heard of Sudoku, please tell me in the chat. But here's what Sudoku is. You have a 9x9 grid. It's a puzzle game. It's a single agent game. So you're just trying to solve this puzzle. And what happens is you are trying to arrange all of the numbers 1 through 9 in these grid cells such that each number appears uniquely in each row, each column, and each square. Okay, so you can see how these thick lines are here. So each 9x9 grid is separated into 3x3 grids. So you want to place 1, 2, 3, 4, 5, 6, 7, 8, 9 within each row, within each column, and within each of these subsquares. So what's happening right now is that I have a solution genetic algorithm running in the background. And so let's go back really quick to the slide for a second, because I want to show you that, that pseudocode again. Okay, so we have this loop right here, repeat until some terminal condition. And while it's repeating, it's just continually evolving the genetic algorithm. So in my user interface, I provide that loop, okay? So this is just going to go on forever. We're continuously running the genetic algorithm. And what we see over here on the right-hand side is a graph, and the graph is being updated in real time. And on the bottom is the generation number. So we're already into like generation 6000 over here. And on the y-axis is the fitness value for each one. So actually, before I get into the Sudoku problem, I just want to show down here that I have a bunch of different sliders that can change the problem that we're working in. So for example, I could increase or decrease the size of the Sudoku problem. So here, for example, the 4x4 Sudoku got solved by the GA almost instantaneously. So here you can see we have 1, 2, 3, 4 in each row, 1, 2, 3, 4 in each column, and we have 1, 2, 3, 4 in each square. So the 4x4 case of Sudoku is pretty easy to solve. Once you go up, and here we have the 1x1 case, okay, so yay, genetic algorithms, they can solve the 1x1 case of Sudoku. But once you get into 3x3 and higher, and this goes up to 6x6, okay? But before I get into the Sudoku stuff, I want to make it a little bit easier to visualize. So what I've done is I've actually programmed in a bunch of different fitness functions. And one of the really amazing things about genetic algorithms is that the same algorithm can solve a number of different problems. So just like alpha beta search, it can, or minimax search with alpha beta pruning, you could use it to play a bunch of different games. Or with A star, you can use it to solve pathfinding for a bunch of different maps. With genetic algorithms, all you have to do is provide a different fitness function, and it will solve a different problem. So here, I've programmed in a number of different fitness functions. So here's one. It's called sum values. And so the fitness will be equal to the sum of the values on the board. So this is no longer Sudoku. It will just, the visualization will look like Sudoku, but it has nothing to do with Sudoku. So if I click sum values, it will restart the genetic algorithm, and it will try to find the array of values such that the sum is maximized. Okay, so of course, what we want is all 9s on the board. And so over the course of just a few seconds here, so we're into about 3,000 generations now, and we've almost solved it, and there we go. So we've solved the case of putting all 9s on the Sudoku board. But of course, you know, you might say this is a trivial problem, but just think about all the different possibilities that there are for this board. So someone out there in the chat, calculate for me how many different possible boards we could have with 9 possibilities for each space and 81 spaces on the board. So what is that number? Anyone out there want to calculate it for me? I can hear the hamsters turning the gears in the brains. So, okay, so someone put up a really big number. I think it's far bigger than that, because it's actually, if there's 81 spaces and there's 9 possibilities for each space, then it's 9 to the power of 81. Okay? So it's 9 to the power of 81. That's how many possible configurations there are, and we found the exact one. Now, turns out that this is a really easy case because it's a convex problem. We talked about that a little bit last time. Here's a little bit more difficult one, okay? This one I call match row. So we're going to increase the fitness by 1 for each number that appears in its own row. So what it means is if there's a 1, for each 1 in the first row, for each 2 in the second row, for each 3 in the third row, we add up the fitness, okay? And look, the same algorithm with the same parameters is solving a completely different problem. It's crazy, isn't it? Similarly, we could have match column. So here I'm going to do the same thing, except we're going to use the columns instead of the rows. Again, same algorithm, same parameters, just a different fitness function. And so the fitness function really defines the problem that you're trying to solve. There we go, solved already. We could bump this up to a bigger one too and see how it does here. Maybe I'll increase the population size a little bit just to help it out. And so you can see with bigger problems, it takes a little bit longer, but you can see the fitness rising over time. So let me explain this fitness graph over here. The blue line indicates at a particular generation what was the maximum fitness of any individual in the population. Okay? So that means what was the single best fitness in that entire population in that generation. The black line is going to be the average fitness of that population, and the green line is the minimum fitness of that population. So we've solved the problem here now, but what I want to do is just restart it on a bigger problem so we can see over time this going up. Okay, so over time, our fitness value of the maximum one is going up, and of course, if we're finding better and better solutions, and our better things are breeding and doing crossover and finding better children, then of course our average fitness is going to be going up as well. And you can see here that our average fitness is actually pretty close to the maximum fitness, which is really nice. But down here in my sliders, I have a number of different variables, and we're going to be working with these variables when we do the assignment. So the first one is the population size. That's just the number of individuals in each population in each generation. The second one is the percentage of individuals that get mutated. So this is going to say, okay, 20% of my individuals are going to be mutated at every generation. Next, I have a percentage of random genes inserted. So what that means is that in every new generation, the new population is going to have some completely random genes inserted. Because what that does is it keeps the gene pool, the gene pool relatively fresh, okay? And what we have down here is a percentage of elite genes survived. So what elite genes are is if you sorted the population by fitness, and you take the top 10% of them, you put those, they just get put into the next generation. So that means that, that means that every generation, the best few are just going to be copied to the next generation. So that way your maximum is always increasing, it will never decrease. So I just saw someone in there say, why the minimum does not grow to maximum when we come closer to a solution? That's a very good question. And so the minimum down here, if you think about it, I am putting some random genes into every population, right? So random genes, if I just generate a random board of numbers, it's probably going to have a very low fitness. So what happens if I reduce this, actually, let's do this first. What do you think will happen to this graph if I increase the number of random genes that I insert to, say, 30%? What do you think will happen? So we have the maximum value, we have the average fitness value, and we have the minimum fitness value. So if I increase, as I increase the random genes inserted, which of these lines will change and why? There you go. So someone in the chat says the average should be lower. So let's test that out. So let's bump this up to about 20%. Okay? So if we look over here, then what's happening, if we're putting in a bunch of random genes, and those random genes on average have low value, then the average value of our fitness function is going to be going down. Similarly, if I put this down to 0, then I no longer have any random genes, and so this line down here is pretty much decided by the random genes. So if I put that down to 0, all of a sudden, look what happens to my minimum, right? It's way up there because without any random genes, my minimum is going to be pretty good. But I do want a few random genes in there just to make sure that every generation I'm getting some randomness in there, because randomness is very good because it means we're trying new solutions, okay? Similarly, if I did not carry over the best solution every time with the elite gene survival, then what's going to happen is it's very possible that every generation I'm actually going to lose my maximum fitness individual. So if I bring this down to 0, what can happen is my maximum fitness individual may be lost over time. So there's no guarantee now that I'm climbing or at least staying at the same level. Okay, so that's what these variables do, and they're very, very important to balance correctly. So you see now how the graph can be affected by these things. So let's reload. Let's go back to matching columns, and we'll bump this back up to 6. And we'll just say random genes at like 40%, okay? And now we can see that rather than the average value being very up close to the maximum value, well, if the minimum value is so low and the maximum value is climbing up, then the average value is going to be somewhere in between them when I have about half of the population being randomized. See how that works? Okay. So someone in the chat asked, what does the genome contain for this example? I'll show you all that happening. I just want to give a demo of the whole program before I explain the details of the program. So let's go back now to the case of Sudoku. So again, now you know how this graph works, right? It's the maximum, average, and minimum values. Over here, what I've done is I have colored the squares based on how many collisions, Sudoku collisions there are, or rule breakings in the board. So if something is white, it means that there are no collisions in any row, column, or square. So for example, the 8 here, this is the only 8 in the column, it's the only 8 in the row, and it's the only 8 in the square. So it is white if there's no collisions. Similarly, or on the other side of that, I increase the darkness in red if there are many collisions, okay? So for example, this 3 here has 1 collision. It has no collisions in the row, no collisions in the column, but it does have 1 collision in the square. So this is the lightest value of red, and it means that there's 1 collision. This one is a little bit darker, and this means that there's 2 collisions. There's a collision in the square, and there's a collision up here. Now, I don't have an example of this right now, but some of them can be even darker where there are 3 collisions, okay? So, the fitness function that I give you by default is essentially the number. If I take each number that's inserted and I add up, like for example, if there's no collisions in a row or a column or a square, I add 1 for each of those. Okay, so for example, this cell up here, the 3 in the very top left, there's no collisions for that one. So there's no collisions in the row, that's a +1 fitness, no collision in the column, that's +1 fitness, and no collision in the square, that's +1 fitness. And so I sum up all of those values for everything on the board. So given that something either has a 0, 1, 2, or 3 fitness, and there are 81 squares on the board, can you tell me what the fitness for a completely solved Sudoku board would be? Someone asked in the chat if I'm going off of a textbook. No. So if you want to learn more about this course, just type !playlist, and you can see all the videos. So go back and watch the first lecture of the course, and you can see what the course is all about. Someone said 324. Well, it would just basically be 81 times 3, right? I think so. Maybe I'm a little bit lying about what the fitness function is, but I think that's approximately it. But we'll go over the code for the fitness function in a little bit, and we'll figure out exactly what it is. So you can see here how it's kind of getting stuck. And one way that you can try and unstick a genetic algorithm is by increasing the population size, or maybe we increase the number of things that are mutated, or maybe we increase the number of random genes, right? So, yeah, 0, 1, 2, 3, obviously. Okay, so here you can see that I'm trying to increase the number of individuals. Maybe I pop this down for a second, so there's not as many elites coming, and now it's coming back up to try and increase the gene pool. So there's lots of cool things that you can do with genetic algorithms to try and get out of these situations where it's stuck. And I talked about that last time. Why is it getting stuck? And I'll show you here in a second. I have to bring up my Blackboard real quick. Oops, my Blackboard has been sort of destroyed. Give me a sec. Actually, just give me 1 second. Sorry about that. I just had to hand the phone to somebody. Okay, so here's what's happening in a Sudoku board. We have, I'm going to show fitness over time. And, well, this isn't fitness over time. This is sort of the solution space of genetic algorithms. So this is the fitness. And on the bottom, we have all possible solutions. So what that means is the following. If I can get my brush size up, all right. Okay, so here is the fitness of all the different possible solutions that we have. And I went over this a little bit last time, but what's happening in a genetic algorithm is that, let's say we chose this individual. And now we're going to reproduce and mutate and make the individual a little bit better. What's happening here is that we're actually taking this and we are going up a hill. So a genetic algorithm can sort of it can be described as a hill climbing type of algorithm, where my fitness is now right here. That is a terrible color. Let's take brown. So my fitness was right here, and now I'm going to improve it sort of in the direction of the better fitness. So what I'm going to do is I'm going to improve it this way. Then I'm going to take it here, and I'm going to improve it in the direction of the better fitness. I'll take it here until I get to this, like the top of this sort of hill. Now, if this is the maximum possible fitness of a Sudoku board up here at like 324 or whatever it was, it's very possible that I get stuck here. Okay, so for example, if I go back, you can see that even though this is still going, I've sort of plateaued at one of these values. Oh, sorry. Here, even though I've been going for like 20,000 generations, this board isn't changing anymore. I've sort of plateaued here, right? So what's actually happening is that I've gotten to what's called a local optima. So this is a local optima. So optima meaning a high or a low. So this is a local maxima. But what I actually want to do is be up here, right? I want to be at the global or the highest possible value. But the thing is, in order to get to here, I would have had to first reduce my fitness. And genetic algorithms do not like reducing fitness. And when it comes to the specific example of Sudoku, you may know as a Sudoku player that in order to take an almost solved board, right, and convert it to an actually solved board, then you may actually have to change other numbers, which temporarily lowers the fitness in order to get to the optimal fitness. So I chose Sudoku specifically because it's one of the worst problems in terms of these local optima. So it's possible that if one of our solutions was initially on this mountain and then started going up, that it may eventually get here. But what we do is, in order to try and make these guys over here sort of hop to other possible local maxima, what we do is this is where the mutation comes in, right? This is where the breeding with possibly random elements comes in. So we want to keep the gene pool pretty sparse and introduce lots of randomness and lots of mutation so that we don't eventually have all of our genes on the one hill here, okay? So someone asked, can you brute force by multiple starting points, or are there too many local maxima? Well, what we actually try and do is when we start out with an initial population, we actually initialize it with the entire population being random, okay? But my graph here sort of, it really is not showing the problem as bad as it really is, because the actual problem is sort of like, this is the space of all things, and then there's one little tiny hill here that actually contains the local, right? The global optima. It's not like, 10 of our original ones would have led to the global one. It's just very, very, it's unlikely that we get to the global optima in this particular problem very, very easily. So what if we are not lucky and we don't make it to the top? Someone asks. Well, then you get this, where you've been going along for 30,000 generations and you don't get a solution. But if you looked at the sum values problem, it's the same problem space, there's the same number of possible boards, but it does solve the problem, right? But you may ask, how is that? Well, it turns out that the problem is way easier than Sudoku, because the problem space of all possible solutions for this problem of summing is what we call a convex problem. There's only one hill, right? So every possible solution could eventually get to the local maximum, to the global optima. So these convex optimization problems, like, for example, even if we change this guy right here to a 1, eventually we could change it back to a 9. Because in the problem of summing all the values, we don't have that sort of Sudoku problem of needing to go back down in order to need to go back up. So all of these ones here, like for example, here's a checkerboard pattern where I'm evaluating it based on their 1s and 9s in a checkerboard pattern, which it is filling out here. Even if we mess up one of the things, we can always fix it again later. So that's what we call one of these convex optimization problems. But Sudoku has many, many, many local minima and local maxima, which makes it a very, very difficult problem. So sort of one of the things about these genetic algorithms is that they can get you to a local maxima very, very quickly, where many other algorithms would just completely fail. Like I said before, this problem, there's 9 to the power of 81 possible positions. If we tried to use breadth first search or depth first search or A* or something to come up with this solution, not a chance. We wouldn't come anywhere close, right? So there are some things that genetic algorithms do very well. And the thing that they can do is get you to a local optima extremely quickly, where other search algorithms and other learning algorithms may fail. All right. So now that you know what the interface is, let's, just like all our other assignments, we'll dive into the code and we'll see exactly what's going on and exactly what you have to do for the assignment. So here is assignment 4. It is very similarly structured to all the other assignments. So in here, again, I have the familiar GUI class and the GA GUI class. So the GUI class is just, you don't need to worry about it. This is just my helper functions. And then the GA GUI class is just how I form the user interface. So this user interface is all set up there in this GA GUI class. Now, all of your solution code will be put into, nope, that's the GA solution code. I don't want to show you the solution code. All of the student code will again go into the GA_student.js file. So this is the only file that you'll submit for the assignment, okay? And in it, I've got a bunch of functions, and I'll go over this in a second, but I'm going to come back to this, okay? So that's the place where you write all of your code. There's a couple of other things here. I've got a Sudoku class for you, and the Sudoku class is going to take in, as a constructor, a size, and it will set up a Sudoku board for you. And inside here, I've got a number of functions that help you with the problem specifically of Sudoku. So you can get and set a row and a column. You can ask the number of conflicts in a row or a column. So for example, the number of conflicts in the row, the number of conflicts in the column, the number of conflicts in the square. It will calculate all that for you. So if you want to use the number of conflicts as part of your fitness function, you can use that function there. Also, I have a set array function. And so, for example, if we want to construct a Sudoku board from an array, we can do that as well. So, as I explained last time, and let me actually bring it up again, here is how our genotype and phenotype is going to work in this assignment. So let me find this. I've got it here. So in this assignment, here is how it works. We're going to have our phenotype, which is a Sudoku board, right? So that's the actual problem space that we care about, the phenotype. And our genotype over here is the representation. So remember, a genetic algorithm needs a one-dimensional array of integers in order to function properly. So we are taking our 2D array of that is our Sudoku board, and we are representing the genotype by just taking that 2D array and converting it into a 1D array. And the way that we do that is just by starting in the top left and inserting them into the array, one by one, right? So we insert all of these until we eventually go to the next row, and these go in here somewhere, these go in here somewhere, and then at the very end, the 0, the 7, and the 9, okay? So the phenotype, that's the problem space, that is the Sudoku board, and the genotype is a one-dimensional array that we're going to be using, and that's like our string of DNA, right? So the genotype is our gene, that is the Sudoku DNA that we're going to be using. So that is the representation. Okay, let's go back to the programming slide. Okay, so the Sudoku board is going to help you, the Sudoku class, because if you have the gene and you want to construct a Sudoku board from that, all you have to do is construct a new Sudoku object and then set the array where the array is the gene. So that's why I've included that for you. And the GUI also helps. Okay, next I have this GA settings class. And the GA settings class contains the GA settings object, all right? And that is going to guide all of our genetic algorithm. So part of the the hard part of a genetic algorithm is once you have your genetic algorithm, it's all about parameter tuning. It's about setting the mutation rate, setting the elitism ratio, setting the random ratio, all this kind of nonsense, right? So what I'm going to do is I give you a GA settings object, and your algorithm is going to pull the settings from this object, and that object is going to get the settings from the GUI. So you don't need to worry about the user interface, you just need to interact with that GA settings object. Also, this is where I define all of those fitness functions for matching column fitness, matching row fitness, the checkerboard pattern fitness, and the summing fitness. So for example, when I pass in an array, so I'm passing in the gene, right? So the gene is the one-dimensional array, and I want to evaluate the fitness of this gene as the sum fitness. So what I can do is I'm going to just have the sum of the whole board equal to 0. I'm going to go over the entire array and just add the value of that array index to the sum and then just return the sum. It's dead simple, right? The sum fitness is the easiest possible fitness. The match row fitness is slightly more complex, but all I have to do is go through and figure out which row that it is on in the one-dimensional array. So you convert the one-dimensional array to a two-dimensional array, you figure out which row you're on, and if the value of the cell matches the row, you increase the fitness by 1. Really, really simple. So these are the fitness functions that I've given to you for this assignment, and don't ever modify those. They're just in the GA settings.js file, tucked away where you'll never see them. Okay? So I've got my solution class over here, which implements my version of the GA. But now what we're going to do is we're going to look through what you actually have to do for the assignment. But first, I want to point you to one part of the GA GUI class that is very important that you may want to have a look at. So right here, where is it? It's in reset, not update, reset. Okay, right here from line 38 to line 47. What happens is this is how we initialize the initial population of our genetic algorithm. So let me move me and the ghosts up here for a second. So the way that the initial population is set up is the following. Okay, so I say this is the first generation. So this is generation 0. And by the way, this reset function is what gets called whenever we change the fitness function or we change the size of the board. You can see how it starts back at generation 0. The other thing that happens when I call reset is that we have an entirely new population, and that's randomly initialized. And this is where that happens, if you want to have a look to see how that happens. So there's a new population. So this dot population equals a new array. Then I'm going to iterate for p equals 0 less than this dot settings dot population size. So this dot settings inside the GUI is where we store the population size. And then I'm going to set up a new random gene. So I'm going to say, okay, the random gene is going to be a blank array. And then for I equals 0 to individual size, and individual size here means the length of the genotype, right? So for a 9x9 Sudoku board, the individual size is 81, right? It's the one-dimensional representation. So what I do is for every possible, or for each thing in the individual, I insert into the gene a random gene value. And so you can call this .settings.getRandomGeneValue. And what that will do for this assignment is it will return a number, a random integer between 1 and the Sudoku size. So whether or not you're using Sudoku or you're using some values or whatever, if you just call this .settings.getRandomGeneValue, it will do that for you. So get random gene value if you want to see how that works. So up here in the GA settings, whenever I initialize a new GA settings, what happens is I push into this array all the different possible values that a gene could actually have. And so I push all the values from 1 up to Sudoku size into this array. and then get random gene value just returns a random element from that array. Okay, so that's how that works. So you don't have to write that function. You can just call this .settings.get random gene value, and that will give you a random gene value. Okay, so that's what I do. And then the other really important thing that you have to look at here is this line right here. So each member of the population is not just a gene, okay? It's a JavaScript object containing two variables. So here's how we create a JavaScript object. We wrap them in the curly braces. The first variable is gene, and that is the gene itself. That is the one-dimensional array. The second value is the fitness of the gene, okay? And so inside the settings function, inside the settings object, we also have the fitness function. So when I'm out here and I'm selecting the fitness function, what I'm doing is I'm actually putting a pointer to the fitness function inside the settings object. Okay, so regardless of what fitness function is selected in the GUI, the settings object will always contain the correct fitness function. So all you ever have to worry about is calling settings.fitnessFunction. Okay. So whenever we put a new individual into the population, we have to put this object, which has two variables. The first one is the gene, and the second one is the fitness. And what that does is, because we're going to have to calculate the fitness of everything anyway, what we might as well do is whenever we insert a new individual into the population, we just calculate its fitness right away. So it's there for us and we can use it whenever we want. So right here, that's how I set up the initial population. And so now every generation of the genetic algorithm, for the assignment, are going to construct the next population. And it's actually remarkably easy. And I've set it up for you to be pretty easy. It's just array manipulations. That's it. Okay, so let me make this a little bit smaller here. And I'll put this down here. So now we're going to go over to your file that you have to fill out. So first, what I have up here is a Sudoku fitness function, but I'll get back to that because I want to explain that at the very end. The other functions that you have to implement are the roulette wheel selection function, the crossover function, the mutate individual function, and the GA evolve function. So the main function here that I'm going to start with is the GA evolve function. And this is the function that takes in the previous population and does the entire iteration inside the while loop of the genetic algorithm. And I know that all of this has sounded incredibly complex and complicated, but trust me, it's going to be the easiest assignment so far, in my opinion. So let's read the notes here. So student to do, write this function. Note, population is an array of JavaScript objects containing two variables. The gene is an array of values, I should say here. That's the array of integer values. And the fitness is a number, and that number is the fitness of that individual. Okay? So population I.gene, that is the 1D representation of the individual, or the genotype, and population I.fitness, that is the fitness of that individual. So that is how, if you have the population and you have an index into the population, you can get the gene, you can get the individual. So here's the entire algorithm. First, set up a new array which will hold the next population. So we just say let next population equal blank array. And it's your job now to populate that with the next generation of the population. Step 2. Step 2 is optional, but it may end up helping you, which is that you can sort the population descending based on fitness. Meaning that if you write some sort of sorting function which compares the fitness, right? So you could do bubble sort, quick sort, whatever you want, JavaScript's built-in sort. And so you would have the highest fitness individuals at the beginning, all the way down to the lowest fitness individuals. It's optional, but the next step, it would make the next step faster, okay? So step 3 is the elite selection. So you're going to add the top N elite, top fitness individuals to the next population. The percentage of elite genes to carry over is in settings.elitism ratio. Sorting the population array by fitness is an easy but slow way to do this. So for example, if we have our array of our previous population sorted by fitness, then what we could do is we could say like let num elite equal, and now we're trying to figure out the number of elite things that we want to carry over to the next population. So settings, this is where we pass in the settings to this function. If we take settings.elitism ratio times population.length, this is the number of elite things that we should carry over from this generation to the next. And of course, we want to math.floor this because we want an integer, right? So then you could say, for example, for let I equal 0, I less than num elite, I plus plus. If we have it sorted already, right, then we can just go from the most elite individual, so the fittest individual, down to the number of elite, adding those to the next population. So let me just do this kind of for you as an example, where we could say if they're already sorted, then population or next population dot push population I. That's it, right? Because if we've sorted population by index 0 being the most fit individual, and it's telling us take the top N individuals and put them into the next population, that's literally all we have to do. The only thing is we have to sort that previous population first. All right. 4. This is the next step. Add the required number of random individuals to the next population. The percentage of random genes to carry over is given in settings.elitism ratio. You can get a random gene value by calling settings.randomGeneValue. Make sure you add the following object to the array wherever adding an individual. So you'd say next population.push gene variable, fitness settings.fitness function gene variable. And actually, if you look back at GA GUI, this is kind of exactly what I was doing here. So if you want to know how to generate a random gene, the code is already there for you right here. Okay, you'd have to modify it slightly, but it's almost the same thing. So over here in your GA student, this is where you have to multiply settings.elitism ratio by population size to get the number of random individuals to insert, and then insert random individuals into the population. And then the last step is the parent selection, crossover, and mutation step. So perform the child generation process, which is as follows. So we're going to keep adding children until we fill the next population, okay? So this entire step is essentially, while the next population is smaller than the previous population, insert more things, okay? So keep generating children to fill up the next population. And just as a little bit of optimization, because we're going to be using the roulette wheel selection, and roulette wheel selection requires summing all the fitness values of all the things in the population, let's just calculate that sum once, and then we'll be able to pass that into our roulette wheel selection, just to save a little bit of time. So the loop is super, super simple. It just says, while the next population is smaller than the previous population, choose parent 1 via roulette wheel selection, and I'll show you this algorithm. I'll show you that function in a second. Choose parent 2 via roulette wheel selection. Then your first child is going to be crossing over the first half of parent 1 and the second half of parent 2, and the second child is going to be crossing over the first half of parent 2 and the second half of parent 1. Then we're going to mutate the first child, and then we're going to mutate the second child. And then you add the children to the population. And just be careful, only add child 2 if it wouldn't put you above the population size. Sometimes that can happen when you get odd numbers, etc. And then what you have to do is you just return the next population. Okay? And remember to change this, because just so your program doesn't blow up, temporarily I'm just returning population, but you have to change this. You have to do exactly this. Okay? That's what you have to do. Just make sure that you do that or it won't work. Okay, so that's literally it. That's the entire algorithm. The only thing you really have to do is take out these comments and then implement these functions. So let's go look at these functions. Roulette wheel selection. So roulette wheel selection is going to select a parent individual from a population based on the roulette wheel selection algorithm that we covered last time. So I'm not going to go over that again. I did an example on the blackboard. So the parameters into that are the population and the fitness sum. And again, the fitness sum is the sum of all the fitnesses in the population, which you need for the algorithm. So what you're going to do is you're going to run the algorithm, which is going to give you the index of the selection, and then you just return the parent, which is the population at the selected index. That's it. That's roulette wheel selection. And the algorithm is literally there for you in the slides. The second function that you have to implement is the crossover function. And so this function is going to take in parent 1, parent 2, and the settings. Okay? And the only reason you need settings here is for the fitness function. So what you do is you're going to create a new child gene. Then you add the first half of parent 1 to the child gene. Then you add the second half of parent 2 to the child gene. So all you do, you go through the first half of parent 1, adding it to the child, then the second half of parent 2, adding it to the child. And just be very careful. The size of the child gene must equal the size of the parent gene. Be very careful of this when parent size is odd and there's not exactly half, okay? So sometimes if the size is odd, then you might have the left half is bigger than the right half or vice versa. So just be careful where you choose that middle point and be sure that your child is the same size as the parent. And then once you've computed the child gene, you don't even need to modify this line of code. Okay, I've already given it to you for you. So here you're returning the individual, and the individual has the gene, which is the child gene that you have to create, and then the fitness is the settings.fitness function on the child gene. And remember that this will always be set up correctly for you, so you don't even need to worry about that. And the last thing that you need to do is the mutate individual function. Okay, so mutate an individual based on the mutation rate. So what you do in here, you take the settings file and you take the settings.mutation rate value. And so if a random number between 0 and 1 is less than settings.mutation rate. So what does that mean? So math.random gives you a number between 0 and 1 randomly. So settings.mutation rate, if the mutation rate, let's just call this rate, equals 0.2, it means 20% of the individuals should be mutated. So if I generate a random number between 0 and 1, right, and if that number is less than mutation rate, that is how I say, okay, my 20% chance has been hit. So if my random number is less than mutation rate, then I mutate the gene. Otherwise, I don't do anything, okay? And if the mutation rate is, if that conditional is fired, so if the chance has succeeded, then all I have to do is change the value of a random index of the gene of the individual to a random value, okay? So for example, if I go back here, I generate a random value inside the gene. So let's just say it was index 1. Then I'm going to take a random number between 1 and 9, and I just insert it there. That's what a mutation is. So I check the mutation rate. If I should mutate this guy, then I generate a random index, and I generate a random number and put that random number in the random index. Super, super simple. And that is it. Except... there's a little bit of a competition in this class, okay? And so there's no extra step for the grad students in this course, but I am going to be having a competition between the grad students and the undergrad students. And I want to see who can modify the Sudoku fitness function because my fitness function is pretty bad. It's just talking about like the number of, if you go back to this, for example, it's just the number of inconsistencies, right? It's the number of conflicts, sorry. So for example, here, if I go to Sudoku and I go back here, then the value that I have for the fitness is just the sum of the number of conflicts with the Sudoku rules. But previous years of doing this assignment have showed me that if you modify the Sudoku fitness function to be more clever, you can solve Sudokus really fast using this, okay? So what I want you to do is modify, and this is bonus material. So you can get up to 10% bonus marks on this assignment by modifying this function to be better. So this is the fitness function that I am currently using in the assignment, right? That's what you see there. But you can also see how my fitness function gets stuck because it's not very clever. And so please, by all means, once you get the GA to work, so once you get to the point where it's doing what my solution is doing here, then go through and try and make the Sudoku fitness as clever as possible. So try and come up with a better one. And that's why, instead of putting Sudoku fitness in the GA settings with all the other fitnesses, I've left it inside GA student because I want you to be able to hand in your own Sudoku fitness function. Cool. So, yeah, that's just a little competition there between the grad students and the undergrads to see whether a grad student or an undergrad student can come up with the best Sudoku fitness function. And what I mean by that is it will be who can get closest to the solution the fastest in the least number of generations. Cool, cool, cool. I think that's all I have to say about this assignment. And I know that I spoke for a long time, but literally, again, all you have to do, set up a new population, sort the array, add the top n things from the previous population to the new population, add a specific number of random genes to the next population, and then perform the child generation, which is already done for you. All you have to do is do these few functions, okay? So yes, I've given you a lot of the genetic algorithm already, but I think that this should be a pretty easy assignment for most people to solve, and it should take far less time than the other assignments. And if you look back here, you have 19 days from today to do that because we've got a lot of material on reinforcement learning to cover. So you have plenty of time, so there won't be any extensions for this one, all right? But if you weren't here at the beginning of class, you do have until... So assignment 3 was originally due tonight at 11:59 p.m., but I've extended the deadline by 2 days, so now you have until Saturday night to finish that. Okay, so I'll be posting assignment 4 zip file on the website soon, and yeah, I will talk to you on Tuesday.